Welcome to the TWIML AI podcast. I'm your host, Sam Charrington.
Hey, what's up everyone? Producer Amari here. Before we get to the show, I want to remind you that our study group for the Fast AI course, A Code First Introduction to Natural Language Processing, begins this Saturday, December 14th. This course will cover NLP applications like topic modeling, classification, language modeling, and translation. To join the study group and the broader TWIML online community, head over to twimlai.com/community. Submitting that form will trigger an invitation to our Slack, and once you're there, join the appropriate study group channel. Hope to see you online.
All right, everyone, I am on the line with Stephen Merity. Stephen is an NLP and Deep Learning researcher working on a startup. I'll let him mention that. Stephen's a longtime friend of the show and was a participant in our conversation back. When exactly was that? It was TWIML Talk 234, but that was all around the OpenAI GP2 release. And we had that great panel discussion about the controversy that surrounded it. But now Stephen's back for a standalone interview, particularly on the topic of his recent paper, Headed Attention RNN, Stop Thinking with Your Head. Stephen, welcome to the TWIML AI podcast.
Thanks, Sam.
Yeah, I'm looking forward to diving into this. But before we do, you didn't have an opportunity to give us a full background when we did that panel. So why don't you share a little bit about how you got to working in this area?
Absolutely. I was lucky to actually start working in natural language processing in late high school. Brilliant professor by the name of Dr. James Curran helps run a summer camp for high school kids. And there he introduced not just programming, but also natural language processing. And back in those days, well before deep learning, it was far more of the traditional methods. But I got obsessed with it from then. So basically, the second I was at university, I was interested in working in the field and published some interesting papers, primarily on maximum entropy models and on combinatorial categorical grammar parsing, if any of the readers, viewers are aware. But since then, yeah, it's been a bit of a whirlwind. So when I came over to the US, I went to Harvard University for a master's, and there I was really obsessed with large data sets, thinking that was the right way to kind of machine intelligence or artificial intelligence. And since I left then, I worked at a nonprofit called Common Crawl, who they basically download billions of pages from the internet every month to turn it into a data set. So think of it as your kind of own small version of Google's data store. Then I worked at MetaMind, which was eventually acquired by Salesforce and became Salesforce Research. And that was where I got most interested in language models. And since then, I've left Salesforce Research and started my own startup called DDX Times. And the idea with that is that I think that language models are amazing tools, just kind of new ways of handling a lot of the computation and linguistic tasks that we think of every day. And I'm really interested in kind of unlocking language as a data set, beyond the kind of surface level work that we traditionally do. So the tagline of the company is, language is humanity's longest running program. And it's kind of accumulated all of this cruft and all of this information over time. And hopefully language models will be the way to start unpackaging that and helping humans actually look at millions of web pages or, hundreds of years of documents without having to read through it all themselves.
Well, since language models will be playing such a prominent role in this discussion, maybe we should start from the top and have you share, for those that aren't familiar with the terminology, what a language model specifically is trying to do.
Absolutely. So the kind of most likely example of language models that everyone has probably run into is the auto-suggest on your mobile phone. So as you're typing certain phrases, kind of highly likely, and instead of you hitting each of the keys on your mobile phone, it'll just pop up a word and suggest that instead. So that's kind of the example of language model that most people see. But it turns out if you keep scaling these language models up, if you use a far more powerful device than your phone, just trying to predict the next token, whether that is a character, a word, or a piece of a word, then the language model, the machine learning model that you produce there ends up encapsulating a lot of kind of interesting pieces of knowledge about not just language, but kind of the structure and uses of language itself. So there have been amazing examples of just predicting the next character on language modeling data sets. One example is OpenAI's sentiment neuron, where they, without giving the machine learning model any extra information, they gave it a number of Amazon reviews, and they asked it to predict the next character. So imagine you're just sitting at the keyboard trying to guess the next character that someone is typing. That's all this machine learning model is doing. But from the knowledge that's distilled in that, it's able to accurately predict whether it's a positive or a negative review. And in fact, when you're generating, you can basically ask the language model, continue generating as if it's a positive or a negative review. So if I was reviewing my headphones, I would say, well, make it positive. And like, the headphones have a beautiful sound, crisp, and very long battery life, But then you could flip it negative, and the language model will say, the headphones have static and are constantly annoying, a slight ringing in my ears. So these language models, as you keep scaling them up, seem to be capturing more and more, at the very least, surface knowledge of text, if not kind of deeper, interesting connections that humans might not be fully aware of.
And so this example you gave, and examples like it, GPT-2 and others, where you're predicting paragraphs and paragraphs, it's all coming from this fundamental ability to predict the next character.
Yes, and in those cases, it's usually the next token, where that might be a word piece. So you might break a word down into, let's say, running, running because, running, or so on. Mm-hmm. But exactly that point is just predicting this next token. And you can, of course, make the task more complex. But it turns out even just providing a huge chunk of text without any additional information about, say, the domain of the text, or where the text comes from, even the language of the text, you're able to start pulling out these interesting details.
And so this paper that you just published, the SHA-RNN paper, tell us a little bit about the motivation for the paper.
Yeah, there are two main motivations for the paper. One is that the language modeling field of late has primarily been dominated by just a single type of neural architecture. So a single type of machine learning model that's being created to kind of solve the problem. And as we've seen from both language modeling itself, but almost every other field in machine learning, there's usually many different ways to tackle a problem. And just as one technique has gotten a lot of advantage in recent works, doesn't necessarily mean we should be focusing all of our time, all of our effort on that. So what I did was, rather than using the kind of dominant neural architecture, which is called the transformer architecture, I used an older architecture called the LSTM, long short-term memory. Many of your listeners probably would have heard of, to get basically quite similar state-of-the-art results. It's still not quite at state-of-the-art, but I also used far less resources, which was the second part. I really wanted a language model that was trainable by the majority of people, because a lot of the more recent language models have required tens or hundreds of thousands of dollars worth of either cloud compute or equipment and so on. So it's really asking the question of, what would this field look like if we headed potentially a different direction in the past, or saw different results and everyone pushed on a different direction? And also, are we sure that we can't achieve many of these results with far less time, far less compute, which will mean that it's more available for more people, more researchers, more practitioners to actually use these results and try it on their own data sets and tasks?
Yeah, you mentioned a couple of things, which I'll take a quick second to point folks to some references from here on the podcast. Back in July, I did a show with Emma Struble, who did a paper on the environmental impact of just the kind of large-scale language model training that you're referring to. As you mentioned, these models take tons of compute to train, and that is all powered by energy and has a huge environmental impact. And she traced that down to the actual carbon load required to train some of these models, and made some comparisons about them. So that is an interesting show for folks to check out. And then we'll be talking a little bit about LSTMs, and of course the authority on that is Jürgen Schmidhuber, and I did a show with him about the LSTM back in August of 2017, TWIML Talk 44. But before we talk specifically about the model you created based on the LSTM, walk us through the transformer architecture that folks are spending so much time on now. What is it doing? How does it work?
Absolutely. So the transformer architecture takes a quite different look at how to do language modeling. I might start with LSTMs or RNNs, recurrent neural networks. And the word there, recurrent, is that it takes a word at a time, and kind of imagine you're reading left to right over a page. Well, transformers have a very different take on this. You get up to a current word. Let's say I've just thrown a page in front of you, and I ask you to kind of guess what the next word would be at the bottom of the page. Your eyes might dart around to multiple different places on the page. And in fact, you might look at first maybe the general topic of the language without looking at many of the words individually or how they're composed. You might skirt around and look whether or not you see a specific person's name. So the general idea behind transformers is that they actually use attention over dozens or hundreds or thousands of the past kind of words or word pieces that you're looking at on the page. And each of these words end up kind of doing the exact same thing. They look at all of the surrounding words as context using attention. So a lot of the time, the most important thing for attention is it'll just look at words that are local to itself. It'll look at the word previous to itself or the last few. But it might also focus on other most likely related concepts. So if you saw the word, maybe a pet name on, not pet name, animal species on the page, you might look for other animal species on the page or something else like that. So this isn't potentially the best example of describing transformers. It's been a while since I've had to try and think through it from kind of the ground up. But the idea is each word in the page would perform attention to get context about itself and about the other words on the page, which also enables you to do some very interesting differences to traditional models. These models usually don't have any concept of what word is necessarily before or after it. It will usually learn that or have some amount of that knowledge injected. That also means you can extend it quite readily to tasks such as images, where you might be talking about pixels looking around, or also audio as well.
So they're not kind of fundamentally sequential models like an RNN or LSTM. They're the relationships between the words are built up solely based on this attention mechanism?
That's absolutely correct. Yeah, there's no sequentiality necessarily forced on it. You can add in a few kind of hints or ideas like that, but it certainly doesn't have the same idea of sequentiality as like a recurrent neural network where you're kind of walking one word at a time. And because of that, one of the main advantages is that you can parallelize a lot of this. So rather than having to walk one word at a time when you're doing processing, transformers can usually perform all of these computations across these words in parallel as well. So there are certain advantages, that's primarily during training, but there are certain advantages about the way in which you can parallelize the work too, because you make less of this constraint on kind of sequentiality.
You kind of mentioned the couple goals. One was to kind of just take on the idea, of transformers and explore whether you could achieve similar goals with other types of models. With that as kind of a starting point of inspiration, how did you end up at a specific model, this SHA-RNN?
In the past, most of the language models were kind of fixed around either recurrent neural networks, but there are also some convolutional neural networks. So almost a similar approach as you would have for handling a vision task. But for me in particular, I appreciate and like the aspect of the LSTM. I think it's more in line with how, at least I can visualize how I would read or think about reading text. And it's certainly nothing to do with how the human brain thinks or whatever else, but it's certainly at least an abstraction that I can think about and reason through. As you're reading text, usually, at least I don't know about you, but I usually go word to word. And I might glance back at a different part of the page, but I'm certainly not, glancing around the page for every word that I'm looking at. And so the LSTM or the RNN are far better fits for that. You have an interior kind of hidden state, so some sort of memory, and you're storing aspects of, the current text that you're reading in that memory and using that to predict the next word. And that I feel is, at least in my mind, a kind of more intuitive fit for how I read compared to, say, these multi-headed attention mechanisms used by transformers, where it's equivalent of, for every word you look at on the page, glancing for some of these models hundreds of times at different locations on the page to pull information back and forth. And they don't generally have this concept of memory as well. Some of the most recent transformer papers have added memory, but it's certainly nothing quite like the LSTMs at the moment, which I feel has kind of, as I said, a far better intuitive understanding of how we'd go through and reading text.
And talking about these two different types of models, we're contrasting the attention mechanism versus the sequentiality, but they're not necessarily mutually exclusive. In fact, you use attention as part of the SHA-RNN, and attention has been used in conjunction with RNNs for quite some time. Isn't that right?
Yeah, and that was one of the aspects that I was particularly interested in actually researching as well. The question of how much of the most recent results for transformers are mostly results of these attention mechanisms themselves, versus, maybe what aspects are missing from previous models. So transformers, they are entirely this multi-headed attention concept, versus LSTMs in the past have generally mostly just been the LSTM and only added maybe a layer of attention here or there, very sparsely. But the research seemed to have stopped in probably 2017, 18, on extending LSTMs this direction. So rather than adding attention heads to these existing RNN models, it was kind of literally the paper that started a lot of this was called Attention is All You Need, which gave kind of rise to this transformer approach. And people have seemed to stick pretty close to the paper's title, using almost purely attention for a lot of these tasks. So before transformers took off 2 or 3 years ago now, I was also exploring using a very simple form of attention on top of these RNN models, and it was referred to as the pointer sentinel model. And the idea is it would allow your LSTM, which is mainly just looking at words one at a time, to look back with like one pass over the page to try and pull some information back. So the kind of intuitive idea was, imagine that I give you a highlighter and you're allowed to highlight some of the words on the page that you think are relevant to predicting the next word. And that had incredibly good results, but it wasn't kind of properly integrated into the model. It was mainly about pulling in kind of rare words that the model might not understand from a kind of information point of view, but it might understand from a positional point of view. So my last name might be a good example of that. Maybe the model has never seen Stephen Merity, but with an attention mechanism, you highlight just Merity and say, well, just pull that word, copy and paste it here. So that was the idea initially behind my pointer sentinel. And that was based off of a lot of work on pointer networks, which were kind of precursors to these transformers or multi-headed attention. But allowing the RNN itself to actually use that to update its kind of internal repository of knowledge, to update its internal memory, wasn't heavily used beforehand. And so that was the direction that I was interested in taking it. And also asking, well, these transform models have had great success with these, dozens or hundreds of heads. How how many heads do you actually need for doing this work, and how complex do they need to be? Is it enough to kind of literally just do one highlight of the page, or do you require 100 different colors for your highlighter and different levels of granularity? And the most surprising result for me is that a single head of attention, so allowing the model to kind of glance back at the page once, is enough to get near state-of-the-art results when you kind of combine it with an LSTM.
And now, is there a kind of measure of the complexity of the LSTM network, like the number of time steps or something like that, that is relevant here to get a sense for, well, complexity?
Yeah, there are a few different directions we could look at. And that was also one of the ones that I was interested in thinking about. A lot of the time, these larger models aren't actually kind of sensible to put into production. They either make a great deal of references, or they require a great deal of memory for keeping, those references in memory, or a great deal of like flops, floating point operations. So basically, the certain amount of compute for your GPU. And yeah, part of the idea was that because I'm using only a single head of attention, and it's a far simpler one, that's the reference to stop thinking with your head, I'm actually able to add in far more tokens into the past reference kind of memory window. So the size of the page, if you want to think of it that way, that you're able to look back over the text, but also that LSTMs, because it's just got this one time step. When you're generating, you're interested in just producing one time step. Mm-hmm. And an LSTM by itself, you have a very small amount of computation you need to do. Versus a transformer, as we mentioned, transformers, at least so far, don't have any aspect of this memory. So every word that they look at, you have to do this full computation over again and look back all the way back over the page, doing a great deal of compute usually.
Is that at both training and inference?
Yes, basically. And it also gets particularly interesting when it comes to inference, because a lot of the parallelization advantages that you had earlier on for training kind of disappear. During training, you already have all of the text kind of, you can cheat and imagine that you were able to predict the next word because you've got this written down text exactly as it is. So it's the equivalent of, I guess, you or me like reading over an existing paper or article, versus when you're generating, you obviously can't kind of glance forward to what you would have written 5 or 10 sentences ahead. And so the model has to step very slowly, one step after the other, even when you have a kind of parallel model as you do with the transformer.
And so the model, you're able to train it on just a single GPU.
Yeah. So all of this lived on a single GPU. Thanks to NVIDIA, they donated it to me some time ago. But yes, a single GPU, and almost all the experiments were under 24 hours. So there's been this huge push towards cloud compute and everything else like that, which there's absolutely no problem with, but they're certainly generally not cost effective. And I generally want my research to be replicable by say a grad student or a freshman, or just someone who's interested and maybe just has the GPU in their gaming laptop. I think there are so many interesting different potential directions for research that it's a shame to limit the field to people who have huge amounts of compute or some way of getting free credits on these cloud services. I've certainly been offered enough of them. There are many companies that offer these credits to try to encourage people to play around, and they'll usually give it to researchers or universities or so on. But at the end of the day, if not everyone has access to those same kind of free credits and free resources, then we're limiting the field and limiting the breadth of people who can contribute.
So you created this model based on attention and an LSTM, and then you ran it against a benchmark, in this case with the NWIC 8 Hutter Prize Wikipedia dataset, and you found reasonable performance with that. Tell us a little bit about the approach to benchmarking you took here.
So the NWIC 8 dataset, it's also referred to as the Hutter Wikipedia Prize. And the idea was that it's just grabbing a partial dump of Wikipedia. So that's the first 100 million bytes or so of English Wikipedia from it's many years back now. I think it was 2006. And this is kind of an interesting data set for a number of reasons. One is that it's traditionally been used for traditional compression. So if you think of zip files or that type of thing, this was the data set that was frequently used to show whether or not a new compression technique was better than past ones. So it has been kind of heavily thought through by a number of different people in terms of traditional data compression. And one of the fascinating things about language models is that they are actually also data compressors. They're certainly not used generally to actually compress files that we might deal with every day. But by being able to better predict the next token, it actually means you're able to spend less and less bits storing the data set itself. And this has been considered a potential demonstration of kind of the idea that compression and machine learning and artificial intelligence kind of wrap up into one thing. Because compression at the end of the day is being able to produce a larger sequence from a smaller sequence because you have some knowledge about the structure of how the data goes together. And in the exact same way, if you have knowledge about, say, the structure of a given language that you're talking in, let's say it's English, or the structure of XML, which is also part of this data dump, you're able to better predict the next token, which means you're able to better compress the file. So this is a really interesting data set in my mind. And it also, of course, runs over Wikipedia, which has already a great kind of collection of all of the world's information in it. So that was the data set that I was interested in exploring. And yes, it's been one of these standard data sets to explore for language models for quite some time. And it turns out with this relatively simple architecture that kind of jumps off in a different direction, my SHA-LSTM, I was able to achieve results that would have been state of the art a year or two ago, unfortunately. But able to achieve these results in 12 to maybe 20 hours, depending on your GPU or depending on the exact formulation of the model. So far faster than a lot of these kind of larger models, and almost with a minimal size as well.
So does the result and performance that you've seen in the benchmarking generalize to other types of tasks? For example, many might be familiar with these transformer models and language models like GPT-2 through just a text prediction type of a task where you give it a prompt and you have it generate some number of words. And to expand on that, often, we're surprised at how coherent that text reads. Would you expect that this model performs similarly on that type of task and generate text that, feel so kind of spookily human?
Yeah, it's a great question. And it's one admittedly I don't have direct evidence for yet, but at least for this model and this data set, when you compare it against the other models, which are all transformer based almost, the numbers are quite similar. And when I'm looking at the output, it's quite similar. The difference would be in scaling. So many of these existing transformer models have run over far larger data sets. The NWIC8 data set is only, unfortunately, about 100 megabytes of Wikipedia. So far smaller than many of these models that are now training over dozens, hundreds of gigabytes of quite varied text. So the model that I use, it certainly produces some fun and hilarious and interesting Wikipedia pages. In fact, I love using it to get the kind of reception, like the New York Times writer said that this article was the most terrible idea in all of existence. Usually this model ends up with beautiful, pithy quotes. But unfortunately, because it's mainly focused on the Wikipedia domain, it isn't as expressive as a lot of these larger models trained over far more varied texts. Now, that isn't an issue with the model itself. That's an issue with the data set that I have. And the fact that I was mainly trying to get it to run quite quickly. But I don't think there is necessarily a limit or going to be an extreme difference in how this model would perform for a lot of these kind of text completion tasks. But you would have to scale it up. And one of the other main centerpieces of the article, the paper that I was talking about, is the fact that because there was so much attention on transformers for the past few years,
No pun
It's those
intended.
models, no pun intended. It's those models that ended up getting a lot of the focus when it comes to both the research, but also the practical engineering behind how to make these models scale. There are indeed certain advantages that just make it far easier to scale transformers. But there are also many known techniques to making other neural networks formulations faster, such as the LSTM, that we haven't actually pursued because we've all gone off in this transformer direction. And I feel like that's a bit of a shame, because as more people spend more time working on a very particular brand or a particular style of solution to a task, these other solutions, which might not actually be worse, kind of fall to the side. And so that's really part of what I was interested in kind of pointing out with this research, that up until kind of fairly recently, these results would have been state of the art. And maybe people have been focusing more on how do you optimize an LSTM, or how do we improve the way it can perform, or how do we scale it up? But that kind of attention instead went to transformers.
When I've played with models like GPT-2 in the past, it becomes very clear very quickly that the model, it's not creating new texts. It's kind of stitching together things that it has memorized and or seen in the past. And these transformer models, because they're huge models, they have a huge parameter space and they can memorize a lot of stuff. So does a smaller model, you've talked about scaling it up. Can it scale up in the same way so that it can remember as much stuff?
Yeah, the concept of scaling up the model, I guess you can go in two different directions. One is you can scale up a small model to handle a larger data set, or you can, of course, scale up the kind of model architecture from this smaller model to a larger one, and also at the same time throw in more data. I guess let's pull that apart. So one is scaling up a small model to a larger data set. There is going to be a limit on how well, at least in the kind of traditional ways that language models operate, a small model will work. There's just some limit. It's not going to be able to perfectly memorize all of Harry Potter if you or all of these different books if you're feeding them in, just because there's a finite amount of space, a finite number of parameters that this language model is able to use. But that's also kind of a different question compared to, can a small model be able to coherently generate text? Maybe especially if you gave it the first few pages of Harry Potter to thumb through. Because we wouldn't call someone unintelligent if, say, I gave the first few pages of Harry Potter to my friend who had never read the book and say, try and continue writing along. If they don't make a reference to Snape, that's a very different kind of problem than them not being able to actually coherently generate text. So we are kind of conflating two aspects of language models. How much can the language model memorize from the world around it? How much of the text that's been written or topics in the world can it kind of cram into its memory? And that's usually the form of parameters. That's where a lot of these models scale. And the secondary question of, well, can it coherently generate text? How much of it is actually some level of understanding of the structure of text or how text might work, and how much of it is actually just kind of, as you said, reproducing what it's already read, what it's already kind of memorized. And I'm personally, hopefully, not convinced that we have to keep scaling these models up. As a human being, if I, gave my friend that task of completing some Harry Potter fan fiction and they'd never read the books before, maybe I could point them to the Harry Potter Wikipedia page, and maybe that would be enough. Maybe they want to thumb through a Wikipedia that's specific to Harry Potter. Maybe they need to read through the book. But I certainly wouldn't have to, get them an extra chunk of brain just in order to handle that type of task. And so that's the other kind of question and hope in my work. Maybe we're scaling up in the direction of being able to memorize more and more of this data far too early compared to having these models potentially be able to refer to new data when it needs to, and thus be able to generalize better. So yeah, I do think that there are two quite different questions, which isn't to say that they also don't interoperate and interact as well. Because one of the fascinating things about text is that it's really, if you think of like memorizing results, humans have spent a lot of time generating the text, and usually text is this beautifully distilled, condensed kind of form of knowledge. And so there is obviously a lot of benefit to that. And there are obviously ways in which that can help a model train. But how much of that is necessary? Or maybe a completely different question is, do we think that these models can generate something that it hasn't read about before? Because that is potentially, there are two different directions we can think about with language models. One is kind of minimizing the complexity of these data sets. The idea that I'll never be able to read all of the internet or all of Wikipedia, but hopefully I don't necessarily need to get to the result or to the information that is interesting or useful for my task. But then the second one is, well, if you want it to generate something, as we've been using with GPT-2 and Transformer XL and a lot of these language models, if we want to get it to generate something that's actually quite intelligent, is it enough to be able to kind of copy together other pieces of knowledge from the past? And I don't know. It's an interesting kind of very open question.
Cool. There's a section of the paper where you go into a discussion around tokenization attacks and that kind of thing. What was that bit all about?
Yeah, so I'll admit this is a section where I'm still having to rethink a lot of what I'm pondering. But one of the questions is that I published one of the standard data sets for this task called Wikitext 103, and generally when you're trying to determine whether or not a language model is performing well or not, you have a specific data set and you get it to try and predict an unknown, like a test section, a section that hasn't seen before. And you ask, how confused were you by, say, all of these words in succession? And tokenization is the idea that you can break these up into kind of different components. You might be able to, say, just split on spaces, and you would consider those words. So running, ran, and so forth end up all being separate. But the other concept is you could break it up into parts of words. So the example I have is specialized, because you have special, you have specialized, specialized. If you break it up into those three different chunks, you can say, well, okay, the word special means this type of thing. When I add the suffix "eyes," I specialize in a field, or I specialized adding the D, an additional suffix on top of that. You can see you break the word up into these components where even if you don't necessarily understand all of one part, you can better understand other pieces. So that was part of the idea behind the tokenization attack, whether it was actually fair for these different models to compare their numbers by breaking up across these different tokens. Turns out I think it actually is. I've been turned smarter people than me have pointed out many of the issues in my thinking. But there's also still an issue when it comes to generating text. So if you've seen from GPT-2, or if you've been playing around with that, or these other online models, most of the time these models are being trained with what we would consider gold text. So text that we would hopefully have pulled from an intelligent source, so it actually makes sense. And if the language model, say, guesses the wrong word next, it can recover because you're telling it, well, actually, no, that word was wrong. You actually meant to say this. But if you've played around with these models and you've had it start to generate something incorrect, it'll usually start, say, getting into this weird loop, or start to repeat the wrong fact over and over and over again, because it says, well, okay, I've seen that text generated. I assume that everything before it was correct, and I'm not going to go back and fix it. So the different sizes of these text chunks can also impact that when it comes to generation. But yeah, the tokenization attack, I've got to admit, is less of a well-formed argument, as it turns out.
It did kind of feel a little bit like you were geeking out and having fun after the real work of the paper was done.
There's certainly, yeah, it was less well-formed than the rest of the paper, so I'll have to admit that much, yes.
Is your hope that folks will build on the SHA-RNN, or, put it into production, put in actual use? Like, what do what's your ultimate hope for this work, and where do you see it going?
Yeah, I've had people already contact me about pushing something like it into production, because there are a number of advantages, especially for production usage, or for if you're running small models. There are certain advantages to it that you don't get out of the transformer. But Honestly, my main hope is for us as a field to kind of think through these two different directions that we're going. One is that we have something that works. We have language models and they seem to work well. Turns out scaling them up, they generally seem to work better. But as we scale them up, we are kind of locking ourselves into two different things. We're focusing all of our research on this one specific formulation of how to solve the task, which we don't know is necessarily correct yet. And we're locking in a lot of our engineering effort into solving the task using that particular formulation, which means that it's more and more difficult for different potential approaches to actually even get a start. The model's slower, or it's just not able to be scaled because the frameworks aren't there and so on. And I am hoping that the community kind of really, really thinks about that, because if we kind of followed this example, I'm not sure if your readers are aware, but like one of the first deep learning examples was the cat example that Google did in, I think it was 2012, where they used, it was along the lines of 16,000 CPU cores to kind of look at small images in order to better classify a number of small classes amongst them, whether or not a cat was in the image. And that kind of sounds crazy now because you can do that on your mobile phone. But that was because we also went a different direction and we realized GPUs were better for kind of solving this type of task. And we've improved the architecture and so on over time. But imagine kind of a different history where we instead focus just on using CPUs like this. Maybe the only people who'd be able to do machine learning at this point were, the Googles or the Microsofts or what have you that have these 16,000 CPUs hanging about. And so the more we focus on a particular direction and forget about the fact that, these models are becoming larger and larger and more unwieldy to train, and that there are potentially other more efficient ways to solve the problem, well, we might find ourselves locked into a future where only a handful of large organizations are able to do this research. And the worst part would be we'd be locked into this future, not because it's the only way forward, but because it's just the way forward that we've all pushed. So that's really my hope for this paper. But additionally, if people use the model itself, I'll be glad to.
So kind of put another way, your general sense is that we've kind of over-indexed on exploit in this particular case, and you're kind of encouraging us to explore more. There's more there to try.
That's a beautiful way of putting it. Yes, we've exploited a great deal, and that doesn't necessarily mean it's the best solution to the task. And the worrying part is, the more we exploit in one direction, the more it seems that all other paths are useless. But that's not necessarily because they're useless, but it's because of the amount of effort put into just, making this one design work.
For folks that want to play around with this, you've got code available on GitHub, is that right?
Indeed, there's code available on GitHub. It isn't the most beautiful code, but I am also going to be rewriting it some point soon with a particular focus on using it in production and using it for a number of different tasks. Because the code base as it stands is really my research code base where you have a number of different options and you're poking and prodding and trying things out, and certainly haven't optimized it for speed, even though it's able to train in only 12 or 20 hours on a GPU. But yes, there's code available. If anyone's interested in playing around with it, as a few have already started doing, please do so, and I'll help as much as I can. But yeah, the code is available, so get to playing.
Yeah, and I just pulled up the GitHub page and noticed that one of the kind of assumptions/assertions that I made earlier was that this model would have fewer parameters than the transformers, and at least in the case of the ones that you've mentioned in the table, that's not necessarily the case.
Yeah, the number on that README page is actually a little higher than it actually is. In the paper, 53 million parameters versus, I think it's 41. And yes, I mentioned that in the paper as well. There are a few different directions for that. One is that LSTMs, they generally need to have a fairly large hidden state in order to kind of retain memory. If your readers are aware of how it works, the recurrence, the kind of forget gates means that it kind of continues left to right. I won't go into too much detail about that. But yeah, the exact, in terms of competing purely on parameters, there are models that are slightly better. And that's really quite reasonable. I also don't think I mentioned the adaptive transformer, which does a fair degree better as well.
Mm-hmm.
But this is more of a proof of concept paper. It's possible that you could kind of trim the SHA-LSTM down to try to catch these as well. But that's also then a question of, do these necessarily train faster? Do they use less compute when it comes to prediction time too? So it's really a bit of a trade-off on a number of different directions.
Yeah. I guess the biggest thing that jumped out to me is that my intuition that the reason why transformers, these large-scale transformers were better at kind of pulling all these texts out is because they had more parameters, but that's not necessarily the case.
No, the multi-headed attention, that's the other thing that this paper is not saying at all. It's not saying that my method is better. It's just kind of asking, how many attention heads are important? How do these necessarily work? Because, I could have well and truly found that, attention heads were the only thing that was necessary for this, but that didn't end up being the case.
Mm-hmm.
But one of the interesting things about these transformer models is if you see those results, the LSTM is only 4 layers deep. So there are 4 LSTMs that you kind of pass the information through. Versus these transform models, the 2 that we were talking about that have lower parameter counts, they have 12 layers each. So you can also either reuse parameters or perform a great deal more computation to potentially get similar results by kind of maybe doing the same task, a few times in a slightly more intelligent way.
Mm-hmm.
And I guess the comparison with that would be either certain compression algorithms, the more time you spend compressing, the smaller the file size. So there are kind of these intuitive ideas as well. So it's possible that by doing a far deeper model that requires more compute, we'd be able to get better results. But that's all kind of open research questions. Yeah.
Were you surprised by the reception to it, or was it in line with what you thought?
Honestly, the reception's been a bit more than I was expecting. The other issue, which is interesting, is, you probably noticed in the paper, I was just having fun with it.
Man.
It's obvious. It's a real research paper, but there's this whole secondary discussion. Some people have gotten very angry talking about the scientific voice and whether or not I was breaking it.
The paper is, how do you put it, quite literary and fun and lighthearted. It doesn't take itself seriously. And, that makes it, I think, rather accessible and interesting. But it sounds like others, you're getting some flack for that.
It certainly ended up being a polarizing thing. In retrospect, I do think I've suddenly gone too far in some directions. And the main point I really wish I had done better was it is less accessible to non-English speakers. And that's something that I in no way ever wanted to have happen.
Mm.
And so that's the main thing I've suddenly decided on. I want to make it far more accessible, which, that might just be additional material, very simplified explanations. As some papers have blog posts that really distill everything out or work through examples one step at a time. But there are kind of 2 other directions that I was thinking about this from. One is that I'm now an independent researcher. I don't have these large companies backing me, and papers are really intensive things. And my natural writing style, the way in which I enjoy writing is, along the lines of in the paper. Some directions, as I said, have gone too far, but other directions people have really enjoyed. And it kind of provided me a lot of room to think about what I was writing, why I'm doing language modeling, what it means to me, and so on. But the other direction as well is that I think in this professionalized setting, I have this entire kind of section in there where I talk about how you'd have to present what I was writing in order for it to be kind of accepted at conferences. Whilst I have gone too far, I think it's also worth it for the academic community to really reflect on what they're expecting and what they're enforcing when it comes to papers. Mm-hmm. One friend said I should, and rightly so, you should be dispassionate when it comes to the scientific voice. You shouldn't put your opinion into it. But just because it isn't obvious on the surface that the given paper has an opinion doesn't mean that there is no bias within that paper. And whether that's the papers it compares against, the approaches it tries, the results it does or doesn't show, I think this is something that the field should actually think about. And a friend of mine said maybe I'm not the right person to think about that or do it, but I don't think that science has to have a singular voice. And I don't know. The main thing as well is that as I said, I'm an independent researcher. I enjoy writing it. That's probably the best way for me to produce more content. So if you want more content, that's kind of the way that I enjoy writing myself.
Right.
And writing pages of text and getting these results is no easy affair. So anyway, that's part of the battle. As I said, I'm still really just thinking through it myself. The next paper I'll try simultaneously turning it down within the main section of the text, but maybe I'll do something ridiculous like put all of my fun asides in footnotes or into the appendix or something else like that.
Maybe you need to train a language model on a bunch of boring archive papers and then run your paper through it or something like that to turn it into academic speak.
Yes, the removal of all the random bits and pieces. Yeah. Maybe or the optional show the hidden text and sections explode and fill out with all the ridiculous expansions. Yeah.
Right. And yeah, I hadn't seen that aspect of the response to it. That's another corner of scientific Twitter, I guess.
Well, yeah, it's interesting. It kind of split depending on community lines. Reddit was the one that was most kind of 50-50 when it came to that. Hacker News had a little bit of a discussion on it, but it wasn't that heavy. And Twitter was, mostly support. The other thing is it's also private channels as well. There are some friends of mine who didn't want to, say it publicly, just because they considered this a mistake I made, and that they just didn't want to. They as long as I don't do it again, sort of thing. So yeah, as I said, I'm thinking through it all a great deal. Maybe I just need to separate out everything and keep the papers boring. But I don't know. I'm still thinking through all of that.
Well, that would be a great loss, but I certainly, there are certainly, as you've mentioned, aspects of the argument that resonate in terms of accessibility, to folks that are less familiar with the particular idioms and things like that you're using.
I mean, at the same time, it's opening up to a broader, like as you said, it's opening up to a broader audience. I had venture capitalists or students that I helped teach in Australia who are still high school students or so on, being able to read the paper and get the vast majority of the content. And then at the same time, a lot of these papers, if we're talking about reproducibility or understandability, I've included my code and people have already reproduced it. A lot of the more complex works, I've spent there was one paper that I spent almost a year trying to replicate. It was some of the worst chunks of my life, because this paper was doing better on a task that I was really trying to solve. It was a language modeling paper. I ended up wasting so much time, so much compute, so much energy. And that was because the authors, even though it was a professionally written and well-received and published paper, the authors didn't include all the details to reproduce the work. That's kind of what I mean by a lot of this is kind of, as I said, my paper is not necessarily the right balance of it, but there's this reality behind the papers that is just papered over. Yeah. No pun intended, but there's this false reality that says we only tried this thing. It's actually, you tried 10 different things and you only reported on that. Or we don't quite know how this works, but we're going to pretend we do for the sake of we're worried about reviewer number 2 saying that this is obviously don't understand how it works and it's not the right, approach or what have you. So at the very least, I think my paper makes it obvious that writing styles are thought about and enforced, but maybe they're not thought about and enforced as publicly as we might need to think about them.
Yeah, well, I think at the end of the day, for a paper one of whose primary goals is to ask questions of the research community, it strikes me as totally appropriate that it, asks those questions in a way that itself asks questions, right?
Yeah, I think that's the other thing. I wanted the opportunity when you're talking about the community as a whole. Like I can't decide on the direction of the community, and I can't necessarily. There are certain things that you can't scientifically prove one way or the other. Like I can't say that we took the wrong direction by focusing on transformers. I can just ask the question, but maybe there's the right way to do that as well.
Yeah, I mean, it's I don't know that it's a right or a wrong thing. It's it's kind of what we've done, and I think. You're touching on that it's not the only way, and I would hope people would get that.
Mm-hmm.
Whether they can get those other ways funded at this point, because everything is so focused on transformers, that's a whole other question. But maybe you've given someone a data point that that says that their thing should be funded.
Yeah, that's the other. I mean, one of the other focuses as well, like. Training language models quickly, my past code base, AWDLSTM, because it was so quick to train, similar times, it was like 12 hours for many of these different data sets. Experimenters were able to, do it in like dozens or hundreds of languages or dozens or hundreds of variants versus these large language models. I know friends who, they set off the training job, and even with, the $50,000 or $100,000 spent on some cloud compute thing, they're waiting 1, 2, 3, 4 months in order to get just one result. I that's the other thing as well. Not just being an independent researcher, but even when I was a researcher who was funded, I don't like the idea that the research in the community is just becoming more and more predicated on you having access to all of this equipment. Mm-hmm. I think there are fascinating questions that your listeners or even like the high school students I teach in Australia, anyone else would be able to ask and actually answer in a completely scientific and fascinating way. Mm-hmm. But only if we keep making sure that these models are actually, trainable, approachable, applicable to the normal person. And a lot of these pre-trained language models that we've been getting recently, where the training, for example, GPT-2, the Salesforce researchers language model as well, many of these different approaches, they're no longer releasing the training code for it. So you get these huge model blobs, GPT-2 XL or what have you, but no one's necessarily able to reproduce it. So any research that's on top of that is predicated on either that company or those research organizations continuing to release those those models, or again, on the idea that you don't have control of the underlying architecture. Like you can't decide whether it's a transformer or an LSTM or whatever else. You have to live with whatever else is put out in front of you. And I don't know, it just, I'm ready to admit one day that, we have to like focus on one direction, or, the compute resources do indeed get this better result, and we can't try all these different things, but I don't think that day is yet, and I don't think that day is necessarily soon.
Well, thanks so much for taking the time to share what you're up to and talk through this paper. Really interesting stuff, and I am really looking forward to seeing what the community does and what you do to kind of extend it.
Thanks, Sam.
All right, everyone, that is our show for today. For more information on today's show, including our guest, head to TWIML.com/shows. Once again, the Code First Introduction to NLP Study Group begins this Saturday, December 14th. Head to TWIML.com/community to get signed up now. Thanks for listening, and we'll see you next week.